In this section, we're going to discuss radical equations and an application of radical equations. So far, we've done a good job of, working with radicals, simplifying, adding, subtracting, multiplying, dividing them. And now we're at a point where we can actually solve some radical equations. All right, down here we have an example of a radical equation. Notice it's just basically an equation with a radical in it. But to solve these, we have to follow some steps so that we can get rid of that radical. So the huge issue is when our variable is under a radical. We need to find out some way to get it from being in under that radical. And basically we're going to use those properties that, hey, for instance, if I take the square root of something and square it, the square root and the square kind of cancel. All right, we're not going to be thinking about this absolute value stuff right now as we see it. But the same thing happens when we take the cube root of something, right? If I take the cube root of something and cube it, then I'm just going to be left with whatever's under that radical. Same thing happens if I take the fourth root of something. All right, I'm going to raise it to the fourth power, and the fourth root and the exponent 4 are going to cancel just like these. So all of these are going to equal just whatever's under that radical. We're going to use this knowledge to help us solve these equations. Now, what we have to do, all right, I have some steps here. What we have to do first, before we start to raise stuff to our power, our index, is we're going to have to isolate the radical. That means get the radical on one side completely by itself. After that happens, we're going to raise both sides to the nth power, and here n is the degree, right? N is the degree. So if it's a square root, raise it to the second power. If it's a cube root, raise it to the third power, so on and so forth. All right. Next, we're going to check and see, right? If the resulting equation doesn't contain any radicals, then we're just going to have an equation with just x, and we can solve it like normal. It might be a linear equation. It might be a quadratic equation, but we'll be able to solve once we don't see any radicals anymore. However, if it does contain a radical, we're going to repeat the process once again. We're going to isolate the radical, raise both sides to the nth power, and hopefully we will no longer have a radical. So this step is it's very important. We'd like to just have no radicals in the first step and then solve for x, but sometimes that doesn't happen. And at the end, what we're going to do is we're going to check our solutions. And the reason why we have to check our solutions is because we're kind of doing something, we're not doing something illegal, but as you know, when we take the square root of something squared, this thing can be positive or negative, or it's supposed to kind of equal the absolute value of x. And so sometimes we're going to get solutions that are extraneous, that won't actually work in our problem. And we'll see some examples here. All right, let's look at this first example here. The cube root of 2x minus 7. We're adding 5 on the outside of that, and then we're going to set that equal to 8. All right, first up is to isolate the radical. Well, my radical is here. The only thing that's preventing it from being isolated is this plus 5 that's on the outside. So I'm going to subtract 5 from both sides. And when I subtract 5 from both sides, I'm going to be left with the cube root of 2x minus 7. Equals 3. Okay? Now that radical is isolated, it's on one side by itself, so I'm going to raise both sides to the index power. My index here is 3, so I'm going to raise both sides to the third power. You got to do it on both sides, and it's only after it's isolated. The third power and that cube root, they cancel, and I'm left with just 2x minus 7, and 3 cubed is 27, right? To solve this for x, I will add 7 to both sides. When I add 7 to both sides, I'm going to get 34. Then I can divide both sides by 2, and I'll get that x equals 17. All right, so this is my possible solution. Now I'm going to check that solution. Okay, and basically I'm going to check x equals 17. I'm going to substitute 17 into my original equation. So I get 2 times 17 minus 7 plus 5 on the outside, and I want to make sure that that equals 8. If it does, then it is my solution. Well, that's going to be the cube root of 34 minus 7. We're going to add 5 to that. See if that equals 8. Well, 34 minus 7 is 27. And just to save some, well, let's just go ahead. That's 3 plus 5 equals 8, which is true. So my solution here is 17. Okay. Had this been false, then I would have no solution. Let's look at another example. In this example, we have x equals the square root of 49 minus 8x plus 7. And we want to solve for x. All right. Again, I'm going to take the same steps as I would before. I'm going to isolate my radical. All right. So my radical is here. The thing that's having me or preventing me from having it isolated is that plus 7. So I'm going to subtract 7 from both sides. When I subtract 7, I'm going to get x minus 7 equals the square root of 49 minus 8x. Okay, so my radical is now isolated. Now I'm going to raise both sides to the index. Of course, there's a 2 understood to be there since we're taking the square root. So I've got to square both sides. When I square both sides, on my left-hand side, I'm opening myself up for a FOIL method. All right, so remember that. Don't try to square the x and square the 7. You actually have to FOIL it out. And that disappeared. My radical disappeared. But here, when I have the square root and I'm squaring it, I'm going to be left with whatever's under that radical. 49 minus 8x. I'm going to FOIL this out, but I'm going to do it pretty quickly. This is a perfect square. This is a perfect square trinomial, so it's going to be x squared minus 7x minus another 7x, so that gives me minus 14x plus 49. And that's going to equal 49 minus 8x. Of course, since my highest power is x squared, what I'm going to do is I'm going to get everything on one side. This is a quadratic equation. To solve that, we have to factor. So I'm going to subtract 49 from both sides. And if I want this side to be 0, I need to add 8x also. Okay, remember with a quadratic equation, we expect to have 2 solutions. Negative 14x plus 8x is a negative 6x. And those 49's cancel. And everything on the right-hand side cancels to 0. So I get x squared minus 6x equals 0. Of course, we can factor. First step in factor is to factor out your GCF. My GCF here is x. After I factor out x, I'm going to be left with x minus 6 equals 0. All right, I have 2 things that multiply to give me 0. I'm going to set both of them equal to 0. So I have x equals 0, or one of my solutions is going to be x minus 6 equals 0. This one's already solved for x. Let's solve this one for x by adding 6 to both sides. We'll get that x equals 6. So in this case, we have 2 possible solutions. And so what we're going to do is we're going to check those 2 solutions. Sorry about that. So I'm going to first start by checking x equals 0. That means I'm going to plug 0 in for x and see if I get a true statement, right, into my original. So I get 0 equals, excuse me, the square root of 49 minus 8 times 0, and then plus 7 is on the outside. Well, I get 0 equals, well, 8 times 0 is 0, and if I take the square root of 49, I get 7. So that'll be 7 plus 7, which is not a true equation, all right? So I know that x equals 0 is not my solution. Let's check x equals 6. All right, this time I'm going to plug in 6 for x into my original equation. When I do that, I'm going to get that 6 equals the square root of 49 minus 8 times 6. And then plus 7 outside my radical. Well, 8 times 6 is 48, and if I subtract 48 from 49, I get 1. And the square root of 1 is 1, so I get 1 plus 7. That doesn't equal 6. So in both of these cases, neither one of these were true in my equation. That means I have no solution. Okay? So you can use that symbol, or you can write the words no solution. Okay, so that actual equation doesn't have a solution. All of the possible solutions were extraneous. All right, and that happens every now and then. Let's look at one more example. All right, in this case, we have actually 2 radicals. And when we have 2 radicals, what we're going to see is that we're going to have to do this process actually more than one time. All right, let's go ahead and do our first step. My first step is to isolate the radical. Well, I have two radicals. Let's say I isolate this one right here. That means I would have to add this radical, square root of x minus 2, to both sides of this equation. And that way it'll be the square root of x plus 3 will be completely isolated. And so now that they're isolated, the index on this radical that's isolated is 2. So I'm going to square both sides. All right, I'm going to get an x plus 3. But on my right-hand side, I have to remember that I have to FOIL this out. And so this gets a little complicated because there's an actual radical in that FOIL, right? So let's go ahead and FOIL this out. We'll take it a little slower since it is complicated. That would be 1 plus the square root of x minus 2 down here, plus the square root of x minus 2. And when I multiply two square roots that have the same radicand, I'm just going to be left with whatever's under that radical, which is x minus 2. Now what we're going to do is we're going to combine like terms, right? These two are like terms. They have the same radicand, and this 1 and that negative 2 are like terms. And so what we're going to do is we're going to leave this left-hand side alone. All right, when I'm going to do these two right here, it's just going to be 2 times the square root of x minus 2 plus this x on the outside, and 1 minus 2 is a negative 1. All right, now I've gone through the process, but I have an equation that still has a radical in it, so I've got to repeat the process. All right, when I repeat the process this time, I'm going to isolate this radical right here. All right, to isolate that, I'm going to subtract x from both sides, and I'm going to add 1 to both sides. Okay, well, the x's cancel, and I'm going to be left with a 4 here. This term, 2 to the square root of x minus 2, stays the same, and these all cancel. All right. Now, I could go ahead and square both sides, but this isn't completely isolated. To completely isolate it, I can divide both sides by 2. Now, I'm going to tell you something here. There are some times where I will leave this 2 here and just go ahead and square both sides. And I'll only do that when this number here isn't evenly divisible by this number here, right? So 2 goes into 4, so I'm not going to have any fractions. Had it had fractions, I wouldn't have divided by 2, and I would have went on ahead and raised both sides to the second power. That's a little trick to help you, or help prevent you from having fractions too early on in your problem. We have 2 here. Let's continue. Square root of x minus 2. Now what we can do is we can raise both sides to this index, which is 2. Square both sides. We get 4 equals x minus 2. And if we add 2 to both sides, we'll see that we get x equals 6. Okay? So that was one of those examples where we had to repeat the process. We ended up with x equals 6. And I'll let you check for yourself. But in this case, this is our solution. It does work out. This is our solution. If you want to write it as a solution set, it would be the solution set that contains 6. There are different ways where I can present a radical equation, and it's one like this. All right, this is a radical equation because radical equations are basically equations with fractional exponents contained for your variable. All right, so in this example, we have 3x minus 4 raised to the 1/3 power plus 9 equals 14. All right, this is exactly the same as saying the cube root of 3x minus 4 plus 9 equals 14. But in some cases in mathematics, we want to have a fractional exponent. In some cases in mathematics, we have the radical notation. All right, but anyhow, we'll do it the same way. All right, I'll have to isolate my radical. So this thing to the 1/3 power is my radical. This is my radical here. To isolate that, I need to subtract 9 from both sides. To subtract 9 from both sides, right? When I subtract 9 from both sides, my radical is isolated. All right. All right, my index here is 3, so I'm going to raise both sides to the 3rd power. That'll give me a 3x minus 4 equals 125. All right, I'll add 4 to both sides. I get 3x equals 129. And I divide both sides by 3. We get x equals 43. All right. You can put that into your original equation, and you will find out that that solution does in fact work. And so if you want to write it as a solution set, it contains 43. Okay, so when you see these fractional exponents, it is still a radical equation. It's still a radical equation. I want to look at one more example, and this is an application example, and one use of why we study these things here. All right, in this example, it says a manufacturer's cost is given by C equals 150 times the cube root of n plus 75, where C is the cost and n is the number of parts produced. Find the cost when 216 parts are produced. All right, so we have this equation here. It is a radical equation because it does contain a radical. All right, C equals 150, cube root of n plus 75. All right, they're telling us that C represents the cost, how much it's going to cost the manufacturer to make those products, and n represents the number of parts produced. All right, so C, and we have n, and I knew that was going to turn green. All right, and so if I want to solve this problem or answer this problem here, I've got to look at what they give us and what they're asking us to find. They're saying find the cost. Well, cost is given by C, so I'm going to find C when 216 parts are produced. Well, this 216 is the number of parts, so I want to find C when n equals 216. Okay, so if I go to my equation here, I'm going to have C equals 150 times the cube root of n, but I now know, or I want to know, when n equals 216, so I'm going to put 216 in the place of n plus 75. And the rest is just simplifying. This is arithmetic, right? Arithmetic. 150. The cube root of 216 is 6, right? And 9 times 6 is 900. And that way we get 975. All right. And of course, cost is normally in dollars, so this is going to be $975. All right. And this concludes our lesson on radical equations.